Right. And uh, so you now should get the screen. Um, I know this is an extremely strange experience. It is a little bit odd. I totally understand that. Um, Now I know that there was lots of support for the idea was is that we're going to do the classes where there would be lots of support based on me coming round, making sure everybody was going and everybody was running. What I intend to do is try do equivalent examples which are based roughly on the examples that we've done in class. So for what I mean is yesterday I did a servo example. I've recorded the servo example. I've uploaded it with the model, and so you can catch back up and see what I was doing. Now I was basing this yesterday purely on looking at extracting torque and looking at if the torque will do the job. So in this case, it was for my Bill and Ted project, and I was looking at if the servos that I was selecting were ideal for what I was tasking it for. I will pick up on the comments, so if there is any comments, any questions as we're going through, I'm well open to these questions. And can I clear that? No, apparently I can't clear them from yesterday, so it's fine. Right, before we continue, what I wanted to do is just show you the teams. Now I set this up. I do appreciate that you're being absolutely pestered to death by teams, but the reason that I wanted to show you this is I have put on a class notebook, and in the class notebook, if there is a particular thing that you do want to share, or you do want to you want me to look at, this is going to be the best way to get access and get me to see it straight away. As if it goes through my emails, I will warn you, I'm having 40, 50 emails a day. And yesterday I had 87 emails in 2 hours, and I just couldn't keep up. So if anybody's continuously emailing, this is not going to be the easiest way to get hold of me. I will, if you have emailed me, I won't ignore you. I will get to you, but it's going to be difficult. Right, so just to show you this, let's take column, for example. Sorry, column. But if I take column, you'll notice here, he's got two optional folders, MATLAB so far, or it's assignment notes, anything that you're working on. If you do want me to see the model that you're working on, anything like that, you can simply go on to the MATLAB so far. 2 minutes. You can, when it loads, you can go onto the MATLAB so far, and what it'll allow you to do is drag and drop any models into there. If I go back onto the teams itself and I go to files, you'll notice on here there is class material. So on class material, you've got the servo zip there. Now, just to show you this, I put that there yesterday just to test to see if this could get on and off. If you've not installed Teams yet, if you've not used Teams yet, you do need to get used to it. As much as we're using this now to deal with the coronavirus, so that we can all interact and still get by, I am told a lot of companies are starting to use this as well, which is quite surprising in many ways. As I said, I am 100% open for any questions. So as we're going through these things, what we're going to do is boost backwards and forwards. If you do have any major concerns as you're going through, please put it on the comments, because I do see everything, and I can feedback as we're going through. So without further ado, I'm just going to open up MATLAB. Now, what I was going to do today was, again, look at other things that are very similar but not identical to that example. I thought what we could do is look at either we could do some gears, which is interesting because that moves towards the gearbox, or we could do a little bit more on the robot arm. So what or we could do a bit of a reciprocating mass build as an example. So you can actually see this process, see how we're extracting values and where these values are coming from and how to present them. So what we're going to do when this actually loads. Yeah. Oh, I'll tell you why that's coming. That's coming purely because I've actually started 2019B. Just to fill you in on that debate between me and MATLAB, I have still not had a straight answer. What's happened to that tool? It's become almost embarrassing of where I'm emailing them and they're emailing me of all these different alternates, and it's like, no, where is this tool? So it's been an interesting one at the minute. Anyway, let's get to it. So what I thought we could do is we could look at I'm gonna have to just give me 2 seconds. Personal when personal comments are in, because I am sharing on single screen at the minute. There's not much I can read. I am recording all this on screen, so everything that's going on here, I'm also recording on screen. Once we've completed this, I will upload it, just because each session I am running are totally different to each other. They are not the same session. I figured, seeing as how Corona's made everybody's life a total pain in the arse, what we could do is I could record these sessions, do something custom, and keep doing these things custom. And I thought one nice example, which what I'm going to do is I'm going to take this onto SolidWorks. We're going to get the parts. We're going to build this example, but I'm going to show you how this is done. So 2 seconds. I'm just going to come into my SolidWorks, and we're actually going to build the single cylinder KTM 525. It's a nice example, and it's a way for us to simplify different ways. Yes. Oh, really? Right. The stream is poor. Yes, I am recording this now, and it will be. How poor is this? Is the screen of poor resolution, I should say? Is everybody else experiencing poor resolution on the screen? It's just to check. I just want to be sure. Okay. Just to answer, Chris, yes, I am. Right. Okay. Yeah. Right. Yes, I am. I am recording it. You can chase this back up, and it will be consistent. So I don't know what's happening there. So apologies. It's just I just wanted to check how this has been received. As I said, I am recording it live, and you will be able to chase this back. One thing that I do need to point out: these comments will appear on that recording, just because my other PC had a bit of a funny turn a moment ago. Just wouldn't open the system. So I'm gonna go to my models. I'm just gonna bring out the KTM model that I've used. So I'll go 525. Okay. So this is actually my research model. I do appreciate that a lot. I find it a bit difficult to get started. It is tricky, and the beauty is I can keep recording, and even if you do log off because you just had enough of me talking, that is perfectly fine, because what I can do is still keep going, and you can catch up. You can catch up afterwards, or you can totally ignore me. It doesn't matter either way. But what I mean is you can still catch up, which is fine. So what we got is this is KTM 525. It's actually an assembled crank. You look at the assembly on this crank. It's a little bit of a sneaky devil. It really is. the materials between it. Interestingly, this is a composite. This is, as far as I remember, is steel, but I need to double check that. What we'll do for this is I've got a simplified compression ring on here, and what I'm going to do is I'm going to actually take it all out as step files, and then we're going to build them all in. So I'm going to right click, and I just wanted to show you this because somebody said to me the other day they weren't clear about how this process is done. So I'm going to right click, I'm going to open. My left side, I'm going to go save as. Now I should tell you, I have never built this in this fashion before. So don't judge me too much if I make a few mishaps. So I'll go KTM 525. This is a tricky one to build because the crank is not as straightforward as we would like it to be. We do need to be relatively clear about where we're translating along and be sure as to how far we've moved. So I'll go crankshaft on 2. I'll call it left. What I'm going to do is zip these together and then upload it to Teams, and then you'll be able to grab what I'm producing. Right, and then if I close that, I'm going through this process. Those of you who've been doing the suspension system, things like that, really will know what I mean by this, of that you're actually having to go through piece by piece to figure out what it is that you're actually going to use. So I'm going to go here, and I'm going to go crankshaft right. For anybody who's unsure, what I did this morning is the videos tend to be quite big. These are 2.5 hour videos. So it takes a while to upload the damn things. And because I use Microsoft Expression, it does take a while for it to be ready to go on. So all I'm doing here is I'm simply going through every single component, turning it into the bits that I need it to be. So if I go here, and then I'll go, let's have a look, KTM, go, oh, sorry, KTM 55, come back in again, I'll go part, and this becomes a crank pin. Again, I've never built this one, so it's going to be an interesting one to build. You'll know that it has to be assembled because this connecting rod is actually cast. It's not a broken one, and it's not fractured as your rods can be. This is your assembled one, a little bit different as normal. I'm recently been told that they've done away with that, and that's been changed. Whoops, Conrad. And then I'm going to close that as well. Then I'm going to go to let's have a look. I'll go gudgeon pin, because if you remember on the original note, on the original assignment, I've given you gudgeon pin there. You have to decide whether you need it. So I'm actually going to put it in there. But do you really need it? It does add certain things. But if you put it on there, why is it there? Have you made sure that it's a true representation of what it's meant to be? My argument would be is that when the piston's traveling from BDC to TDC, which is bottom dead center to top dead center, my argument would simply be of that there is rotational momentum that appears around the actual joint here. In your assignment, I am not marking towards that degree, or else that would be a total tyrant. And don't get me wrong, it is meant to be a difficult assignment, but not so difficult that it leaves you with a migraine. You'll notice I've marked it up as normal, 94.45 millimeters. Again, that's literally how it's machined. This is my but basic oil control ring. Anybody who's into engine rings, you will know that this is actually an assembly. But I needed something there to give me a little bit of flexibility. So I knew where everything was sitting. So I'll go back onto here. and onto the steps control, and we go to here. And I'm nearly there. This is all I'm doing is I'm deciding what parts I need. Now you'll notice at the start, even before we did anything, instantly did away with the cylinder. Arguably, now this was just me closing the ring because I was being anyway, but arguably, do you need the cylinder? You don't need the cylinder. You wouldn't need the cylinder. What we're essentially saying is that we'll control that cylinder for certain behaviors, certain displacements, things like that. Right, so that is our assembly. Now, the reason I've gone through this process of just exporting is that is in essence what I'm actually asking you to do. Now, what we're going to do with this is we're going to approach this step by step, and we're going to try and figure out what's the best way to actually build this and place an axis. As some of you will be becoming now very clear, when it comes to axes and it comes to performance like this, applying an axis is incredibly tricky. Applying multiple axes for something like a V-twin configuration is very tricky. Like I said, if you are interested in the control side from the robot arm, try the servo. I was taking people through the servo yesterday. Again, that is on Blackboard. All the notes are on, well, I say notes, the video is on there with the actual, the model that we built. This, again, I'm recording this, so this will be up there too. Any model I generate today will be up there too. I am frightened that I'm going to run over, and I won't lie, I probably am going to run over, because you know me, I like to... oh, you've lost all the sound. Oh, that's a shame. Go. So there's a few that have been losing sound and quality. It's all right. We're going to still continue, just because, again, this is being recorded. So at least then I can upload this and you can take a look at it. It's a bit frustrating that you've had that experience. I do apologize. You know, it's a pain in the backside when that happens. So I've just shrunk that down because I can come back to these questions as we're going through. Right, so I'm into MATLAB now. These models here, what I'll do is I'm just going to highlight them, right click, I'm going to add them to zip. So it's zipped. And if I go into Teams, what you should now be able to see when I upload this, you'll instantly see KTM 525. So I'm going to drag and drop. Huh. That's very strange. Try that again. Whoops. Right, so I don't know what the hell happened then. Something went horribly wrong then. Let's try this again. Let's connect back up. Yeah, wow. I don't really know what happened then. Apologies. It's probably me messing and fiddling. It's probably me. Anyway, you've got the 525 there. You should now be able to download. Sadly, it's actually just recorded that's happening to me, which is very awkward. Right, so what I'm going to do is I'm going to navigate to that folder. So I'm going to navigate over to the folder. I'm going to come into the KTM and then click select folder. Now, if you remember what I said before, is make sure that you add this as a key point. So where we've got KTM 525, I'm going to right click, then add to path, selected files and subfolders. Right, so we're in, and double click into there, and then what I'm going to do is now start on the model. Before I start, has anybody had any issues with getting MATLAB started? Has there been any problems with MATLAB at all? Has anybody had any problems with getting it working at home? If this does come up, by the way, please message me, get in touch. I will try and fix that and solve that as soon as I can. So, I'm going to go new, and I'm going to go Simulink model. Again, typical procedure of what we follow. And I'm going to go create blank model. Span to there, and then what we'll do is we'll go Simulink model, and we're going to go library, then we're going to begin. We're going to Simulink, we're going to models. Now, obviously with this, I can go relatively quick. You can always catch back up afterwards, so I'll go utilities, I'm going to drag and drop solver configuration. And then we're in. And now what I want to do is go to mechanism configuration. And then what we're going to do is go to frames and transforms. I'm going to drag and drop my frame and transform. Now don't forget, when we're putting these in, we need to offer this as a reference point. That's all it is. So I'm going to spin that round, and then I'm going to connect that up. I'm going to bring that to here and connect that up. Now, this is the tricky bit. This is why I thought it'd be quite nice to do the KTM, because getting used to assemblies and getting used to how the KTM operates and getting used to how components interface with each other is incredibly useful. We have a predefined assembled interference fit crank, so we need to think about how it's going to interface. So first things first, we know from any engine system that it's going to revolve around the crank. That's how we've been building it. So I'll drag and just place that into position and bring that into line here. So this will be our actuator. So I'll rename that actuator joint. Hang on a second, I'm spelling that totally wrong. That's winding me up. It's because stuff's not working for me. Yeah. Better? Right. So I'm going to go actuator joint. And now what I want to do is bring in a body. So I'm going to go bodies. And with this, we discussed this before, we'll go file solid or solid. I'll stay with my solids for the minute. A person said yesterday, can we do both? Of course we can do both. We will do both. So let's go crank left. And I'm going to copy that. This is obviously going to become crank right. And then I'm going to copy that, and then this is obviously going to become crank pin. So then this becomes our assembly. Now I appreciate that. I realized this after yesterday, we've not done much on assembling these things. So I'm going to double click in, expand that out, and I'm going to go to file. I'm going to navigate to my file, and then I'm going to go for crank left. And I want this to be movable. I want you guys to be able to open it. So I'm just going to remove that. And then I'm going to F5. If you remember, at the beginning, I already added the file to file and subfiles. What I'll do is I'm just going to set a default density. Well, let's go through the proper procedure. So if I go to crank material, so come on to crank material, and then if I go to crank material, let's have a look. So they're suggesting a steel. Now I am just quickly looking for a value here. So let's have a look at the rods and the joints. And what's that material suggesting? Materials loads and crankshaft. So according to this, so the mains, joints, 2 cranks. So we'll assume it's been forged in this particular method. So they're suggesting a steel. So let's go with a steel. So I'll go with an RR58. No, I won't. No, I won't. I'll go with just a steel for this. We can change this as we suit. So steel density. So steel density, Google 8.05 grams per centimeter cubed. So I'm going to go down, drop that 8.05 and update. So that then puts things into play, and then I'm going to F5 just to put that into position. Then I'm going to go frames, and I'm going to I just want to turn on my frame toggles to give me an idea where everything's sitting. Interestingly, if you look at where that sits, we could probably use that, because if you're spinning, you see there, it's actually ideal. We need to be relative though of where that's going to and where the actual conrod's going to sit. But let's put that. Let's be happy with that. I'm going to add a frame on to put the pin into position. Now with this frame, what I'll do is I'm going to use the edge. So I'm going to left click on the edge of it. I'm going to call this a pin connection. Based on geometry, and I'm going to apply. Again, we've got that Z acting down the actual pin joint, which is exactly where we need it to be, because we're going to have that revolute behavior continuous like that. Now, keep an eye on my datum. My datum is exactly, I want everything to try and stay relative to that datum. I don't want to go too crazy, or else it's going to mess with how I assemble things. So I'll go save, and then apply. Then click OK. Right, so we've got the left side. I mean, arguably, if I right click and then drag across and turn that into crank right, sorry. So we'll go crank right, and then just, yeah. It's complaining because I've already got it. So if I go crank right, go right, then delete that out. Now we've got that relation between the two, so I'll come back in, and I'm going to navigate myself back around to my crank right, and then go OK. Just out of curiosity, has everybody been able to get onto Teams to download this model? Just gives me a moment to pause as well. Got any burning questions about what it is that we're doing? Brilliant. I just thought I'd check, that's all. Has anybody got any? Has anybody got any burning questions on this so far? The real thing with this is we need to ensure that the axes stay around right, but we need to be clear about where it's going to move, because we're going to have to translate that center axis, if you remember. Now, the reason I'm going through this, the way I'm going through this, is it allows us to really dig deep about why we're translating. Now, this is a bit of a trick. I always like to do this. So if you look here, I've got 8.05. It can be such a pain in the arse going backwards and forwards, backwards and forwards. Now, I'm sure Akinola may have shown you this, but I'm going to show you guys this anyway because I found this easier. So I'm going to go Model Explorer. It's not something that's really heavily for the assignment. It just can make life a bit easier, that's all. That's all. So you see here we've got Simulink Route, we've got Untitled Model. If I go to Model Workspace, this is the internal model workspace. So on here, if I click this, this is add a new MATLAB variable to the internal model workspace. Again, don't worry, I'm going to give you this anyway, but it can be something quite useful. So what I'll do is go let me just double check. Yeah, 8.05. Yeah. Right, and you see here, it's coming as 8.050001. However, if I right click, rename, and call this steel, just bring that value back because that's very irritating. Okay, that's fine. Let me just apply that. Right, so what you see there is that's applied. So if I now close this, come into here, now where we've got inertia, if I type steel, and then click update, but I do F5. Have I used an uppercase with that? Have I done my ultimate rule? Oh, I did, right? You know when I type steel then, I've actually inputted it as an uppercase S. This is literally what that's complaining about because I've done a lowercase here. So if I go uppercase steel and then click apply, then go F5, what it becomes is a variable. Now, it's all right for just this, but if I click apply and then close, but then if I go to the right one, then do the same thing again, and type steel, and then do an update. What it is now is there is one variable embedded in the model that I can just refer to, and it makes my life so much easier because if I come across multiple components made of the same thing, I can just refer to it as a value, and I don't have to keep putting it in and putting it in every time I start the actual model. So it does make life so much easier, so much easier. Come down to frames, and I'm just going to check where this pin connector is. As ever, because of this being a multiple layout, what it's looking for is the curve at 77. It just means that the curve at 77 here actually exists there, which for us is totally incorrect. So if I come to the upper edge here and then go select, now what we got is we're looking a bit more in a healthier stead. Now let's try and just get this crank pin together, and let's just take a look at this, if this is going to be any use or not. What I'll do is first, now if I come back, just look at this again, expand this out. Now I'm actually going to use this point as my world to revolve around. Both of these refer to the same particular point in axes. So what I'll do is I'm just going to connect, no, that's not, that's the wrong way around. I'm going to connect this to here and just revolve that up, bring that down, or maybe bring that across like that. Then what I'm going to do is just look at the crank pin. Now the beauty is with having this type of construction is if I'm going for the crank pin and then I drop it in like that, and then if I come to my original crank pin and I just remove all the residual data to it and then go F5. Now I'm in the same position again. I can either use what I'm now building, which is a library of materials, so I could just simply go steel which for this I will, but I can come back and change it to any particular library that I start to update to, if you know what I mean. It does make life so much easier, and it does make things consistent. So you can say, that's what this is made of, that's what this is made of. As for this, I think the crank pins actually don't tend to be steel. They tend to be, I think they're a composite aluminium, but I'd need to double check that. For this, we'll presume it to be steel. I do know that the gudgeon pins will be anodized steel because the weights of them, they are monstrous. Right, now this is a connector. So what we're going to do is decide how in the hell we are going to connect this to the crank. What I would say is we're going to try and match to both sets. So I'm going to select, click apply. Now we'll call this link left. Save. And then I'm going to apply another one to the other side. Based on selection. And obviously we'll call this link right. Now the reason I'm doing these is just purely because I want to make sure that both sides have a point of reference. Now, if I go to my R values, arguably where link left sits and R sits, arguably, do we really need it? I would probably say no where link left is. So I'm going to drop link left because I think I've put too many on there. For drop link left, we see that we've got this consistent flow between the two, and we're now ready to move to the next phase. So if I click OK, and if I drag this out just a little bit, we know that link right's there, link left is there. So I'll flip this round. Don't forget it's Control and R. And I'm just going to connect these up and make sure it's looking like it should. Because you know what these things can be like. We start off and start running them and come away and go, what the hell is that? So let's come back, and then let's just run it. Shit. Okay, so where did I go wrong? Let's take a look. Crank pin to a crank pin. I've connected it there and not there. So let's just delete that. That was my mistake. I come into here. Right, and then let's run it again. So now we have a nice consistent assembly. Oh, hell. No, we don't. Still don't have a nice consistent assembly. So we're still in a position where it's not working like we wanted it to. The back end is to give equivalent for when it's rotating around, and it will do as it's told, because in essence, this one is just going to follow with this rotation. So what we need to do is go back and re-examine what I did wrong. I say what we did, just me really. Click onto here. This is my crank right. So let's take a look back onto crank right and take a look at the actual perspective. So if I go onto my toggle toggle frames, this is where the axis is actually not working for me. This is where the axis is actually working against what I'm trying to do. So if we flip back again, you'll notice here, because if you look, this axis goes in like that. And then if we come back to the crank pin, and then we take a look at the crank pin, we open up the crank pin, and then let's just spin it round for the same perspective. It does really help to spin it round. So it's like this. If I add these on again, you notice now these are doing the same thing. So one way that we could try and fix this is where we've got the link right. What we could try and say is, anybody who's proficient on CAD, you will know this as when you do counter fixing. So if you can fix, you can constrain one way, or you can flip it round and constrain the same way, but in reverse, if you will. This is a similar process, just it doesn't exist as that type of restraint. So I'm going to edit onto here. Now what it's saying here is my positive Z is that particular axis that I'm interested in. Let me just close that. My positive Z is that particular axis that I'm interested in. So what I'll say is my primary axis for my positive Z is actually going to move on my negative Z. So if I click OK and apply, let's take a look, see if that's fixed it. It may not have fixed it yet, but it may be one step closer. So now what it's done. So now what it's done is it's now aligned it. Oh my God. It's now aligned it in mirror perspective. So if you imagine it's rotated from this particular axis 180 degrees. So now what I want to try and do is flip this again. Now what I'm going to do is try and change this Z axis to come in this direction, which is the alternate direction. So this will be done on the crank pin. I mean on the crank itself. So we'll come back to the frame where I'm connecting to the connection. What I'm going to do here is say make that. Oh, I want to move that along my negative. Then save, apply. Right, and if I rerun again, now you see this button here, this is really useful. This is update diagram. So if I run it, it'll run it again. Now what it's done is, because I've obviously counteracted between both changes that I've made, it's actually just flipped it back to the original perspective, which is not so good. So let me just try flipping that to there, click save, and then apply. Let me just see if that'll allow us to flip that round. No. So now we're at a little bit of an awkward one. So I'm going to bring that back to there, and I'm just going to hit save for a second and then apply onto that. Now what I'm actually wanting to do is I'm just wanting to reset this to get it back into the right perspective. Some of you will, hopefully some of you should have really faced this at the minute. It's a real pain in the backside when this happens. So, let's have a think. If I come back to my crank pin, and I will just realign that back to remind myself where the hell I was going with this. Click, I'm going to just apply that and then upload again. So that's where I was at. So in these states, there's a few things I could do. I could just get annoyed and just flip the damn thing 180 degrees. So if I come here, for example, and where my Y is, if I attach a Y to this, so what I say is the relation between here to here is a rigid transform. So let's go rigid transform. Let's go utilities. And then I will go to forms and transforms, bring this across, and then I'll bring in a rigid transform. Rigid transform will solve this in one single hit. Now don't forget, base is where it starts from. The follower is the result. So, or back and front. So base is where my initial position sits, and the follower is the result. So I'm going to go rotation. I'm going to go around Y, and I'm going to make that 180 degrees. Then apply, and then OK. So if I run it now, it then puts everything in the correct assembly. The reason I can do that is because my predominant thing here, the major element I need to be considering here is the relation along here and up. Is that right? No, it's that one. The relation along here and then travels upwards. So I need to make sure that I'm getting that rotation that I should be getting, because we don't want to get all the way through this process and then go, oh, Not working. I'm not going to use R on this side, so I'm going to drop R and then apply. So what I'll do is go to my physics, and I'm just going to move my gravity to be active in Y, and then apply. And then all I need to do is just run it. Test it a bit more, I'm going to actually put some revs on and see if that is what the restraint is going on between there. So run it again. Right, so we know that it's actually moving like we want it to. So it is moving in the right process, which is great. So if I come back to the crank pin, this is where we need to be relatively clear about where we're going to move to. So I'm going to go to frames and transforms. I need to add a central point of axis that I can connect to. So from here, it comes in as ever and then just gives me the last known position it knows. What I'll do is I'll select the top. I'm going to call this big end. Then go based on geometry and use selected. Now again, the pin is, we're going to rotate around that pin, and that's what's going to be our big player. So you can rest at ease that that's how it's going to work. It's dead straightforward, but you just need to keep that in mind. Before I push on with this, is there any questions on what I've done here so far? I know it's a total different approach to constructing the engine, but it's not quite the assignment. But I thought it'd be nice because it's a revisit to. This is a lot more of a more trickier example as opposed to the Aprilia, the straightforward Aprilia. This is we're using things that you're not really too comfortable with, and I wanted to do these because it just helps for you and your understanding. So if there's any questions, please fire away. If not, nope, 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 nope. Good, right, brilliant. So I'll just drop you back down because I don't know if you see my Adobe Connect thing here, but I see you. I'll click apply, and then we're going to go like that. So I've turned on my datums now. I've got 3 points of reference. Now you should really start to see what, in essence, what I'm essentially doing is I'm building a replica of how the Aprilia was constructed. All engines function the same methods. They all have the same relations to each other. Now, I'm sure somebody, one of you, must be thinking to yourself, but what about the central moment of inertia when they're actually constructed and assembled? They'll be different. If you have a different material, at the minute, what they'll do is just relate to each other like they are one single material. But this is an assembly. This is definitely assembly, and there's nothing to tell the system that they are two separate components. How I can hear you screaming down your screen? Well, maybe not. How can you actually tell these differences? What we can actually do is say to this, what these are is they have, think of this as bonding. Membrane ANSYS, where you bonded the relation across multiple points. This is the same principle. So if I go to my, where is it? There we are. If I go to my Simulink library, now what I'm going to do is I'm going to go to my joints. Within my joints, I'm going to drag and drop a weldment. A weld joint, all it literally does is it just says these are two components together working together. That's all it does. There's no sophistication with it. There's no special axis. There's no, dare I say, just jargon to go with it. There's no like secret thing that you don't know. It literally just says these two parts work together in this relation. Now, because of this type of assembly, because you must admit what we've visited so far was not this type of thing. So if I run it again, you'll notice it does nothing. Oh, let me go run, sorry. You'll notice it does nothing because all it does now is just says, oh, these are separate parts. To allow me to be clear about where these things are moving, though, I always, when I'm building these models, because I build a lot of these models, I always just give myself a change of color. And I know, I mean, just because I'm comfortable, I'm going to make it pink. Well, I've got a laugh, no one else will. So now if I run it, just be sure that that everything's relating as it should be relating. Right, so let's move into the next bit. We've now got fully constructed KTM 525. Well, I mean, some call it the 530. Anybody who's in motorsports, you'll know this, but yeah, some call it the 530. I don't know. I really stopped caring. You know, after a while, you just switch off. That's what happened to me. You kind of go, yeah, it's good, that, isn't it? Right, so so I'm going to go to my Simulink library, and I'm going to drag and drop a Revolute joint. Bringing in the Revolute joint, and now all I'm going to do is bring in the comrod. So let's drag and drop. Well, in fact, I've done so much with that, I'm probably just going to use this and call this comrod. It's just because the crank pin has got multiple relations. So call this conrod. This becomes comrod, and double click in. And like on the other one, what I want to establish is big end and little end. So I'll go comrod, apply, and then I'm going to drag all that back. This is incredibly useful if I want to move things around. I mean, I know I keep talking about it, and I know it's getting very irritating, but I just keep saying it because it is really useful. It's really useful. So there's this comrade. Let's put in some frames. Obviously, big end, little end. I'll go to my R, see where we're at. Look at that R. That's well useless. So what we'll do then is I'm going to drop my R completely. Don't need it because it's not going to serve me any purpose. I'm going to go to my pin connection, which I will rename. I'll call little end. Select onto here. I'm going to go central. I know it's a little naughty. I am going to go central, put it on there, and it gives me a nice key point for reference. So I'm going to use selected. I should point out as well, if anybody has already installed 2019B and you're struggling to get that bloody toolbox working, totally understood. You know I'm in that debate at the minute with MATLAB. You can overwrite it with an installation of 2019A. All you do is just reinstall it all again. Normal procedure. And I'm told you can even go back to 2015, but you don't need to. It's just a point. The other thing that we need to consider about this application now is Z is in that little end. Fantastic. Yeah, it's a good point, Adam. 2020A. Now, I've not even reviewed 2020. God, I sound like a YouTube channel. I've not even reviewed 2020A yet. Somebody told me literally yesterday that this has now become a beta access. My intention is today to get it downloaded, get it installed, and take a look at it. If this resolves all these issues that I've been finding, that'd be fantastic. Now, if you're curious about doing it, you will be doing it on your own beat at the minute. But I do intend to do it once I get a straight answer whether then tools are there or not. In fact, let me just check my main PC. I don't remember installing it, but I'll just double check. So if I check on my main PC, no, I never did. It is on my intention, but I would recommend just holding on for a minute. Let me install it and take a look and see if that's right. And I will get back to you. The best way I can get back to you, as I said at the beginning, I'm quite flooded with emails at the minute. What I'm going to do is use Teams, and I will do a blanket email, a blanket message to everyone, and let you know whether I can find that tool on 2020A, because if it's there, happy days. It's the answer to all my problems at the minute. But I will get back to you with it. That's the best answer. I'll go on to new frame again. And I'm just going to select onto here. Now, this is quite interesting for me. As I said before, I've never built this model before. So I thought it may be a joint learning experience for all of us. I'm going to go big end. And go you selected onto there. Again, Z's in that particular component. So this for me is dead straightforward. Now, just because, again, it's going to be connected with other components, I'm just going to change its color. I don't want to make it too close to the pin, or else it will get confusing. So I'm going to click OK and OK. And then what I'll do now is I'm ready to connect my little end to the Revolute. So what we're looking for is that stereotypical, how do I describe it? That stereotypical pendulum. I don't know if that's the best way to really give that a description, but I think pendulum would be the best way of describing it. Sorry, something just fell down. 1 minute. There we go. So I think pendulum will be the best way to describe it. So let's run it. But don't forget, it's under very zero resistance, and also at this point, the com rod has actually not been assigned with the material. So let me just find aluminium. Oh, 70, 75. Let's go density. 7075 was used by Honda at one point. So look at the density there. We've got 2.81 for, and this is a 775. So I'm going to just copy that as a name. 2 minutes. Everybody's ringing me now just to discuss bloody coronavirus. You know, you just think I could not give a shit at the moment. Right. Just so annoying. Right, so what I'll do now is drop in, and then all I've done is gone back to that model library again. Again, the beauty is with recording. I should have done this sooner, to be honest. The beauty is with recording, I can move relatively quick. It's a 2.81, so we'll go 2.81. Right, so I'm going to close that back out. Come back into here, and because I've got the name on save, I'm going to put that into there, and then this is underscore. Let's just try it for density. Normally, if I put onto density and it gives me a value, 5. Oh, mistake. Right, so I'm going to come back to the actual frame. What did I do wrong? I'm guessing I see here, got underscore, and then it's an underscore. It's replaced my dash with an underscore. So all I need to do is come back onto my dash, no underscore. Apply, 5, update, 5. It is just a nice way of doing it. Makes life so much easier. Because what you end up doing is building that library. Which is ace. I'm going to drop that out for a minute. I just want gravity to take effect on what's going on. So I'm just going to remove my revs as well. I just want to make sure that... See? As daft as it looks, that is what we're looking for. The way that this is designed, the counterweight here, it's phenomenal. I love this type of stuff. I love how this has been designed all round, but this counterweight here, this is a typical construction of what you'd find on two strokes as well. Very, very similar. Right, so before I get on to very nerdy stuff, I know I'm going to use another Revolute joint, because if you remember on the assignment, what we got is we've actually got a gudgeon pin. So whether you use it or not, it is entirely down to you. You can choose. Arguably, if you were doing gudgeon pin study and you were looking at the momentum that's caused from the torque that emerges, the very, very tiny bits of torque that emerge around the gudgeon pin, then, you know, maybe it does need to be there. Maybe it doesn't need to be there. This, interestingly, the gudgeon pin is a big debate. You do come across people who drop it because just say it's negligible, and then you come across these really pedantic people who literally say, oh, well, actually. So you really need to decide exactly where that's going to go. That's why I've put it there. Now, for me, I'm actually going to put it in there. I'll put it in there, and then we'll take it from there. We might not need it. We might need it. In fact, no. Let's drop it. Let's be controversial. So I'm going to drag and drop another connecting rod, and I'm going to go piston. So let's bring in the piston. As you're probably well aware, this is where it's going to get tricky. It depends how it's been drawn. Depends who's drawn it. Now, I do remember when I was first putting this together, I did have some issues. So I may have drawn this from the crown. The crown is known as the top of the piston. I'm going to F5. We'll probably need to change. Arguably, we may need to change that density. But so I'm just going to remove my connections as well. So I'm going to remove that, and go F5. Right, so let's take a look at where it sits. I won't lie, we're very lucky, really. It's sitting there. When I was studying this originally, because I should say this is what I drew for my PhD. I tried to even pick up on, I don't know if you can see him. I used the CMM to even give me the chamfer that takes into consideration, because if anybody's unsure, I'm going to try my best not to get nerdy here. This chamfer tries to deter as much surface damage on the cylinder when it's tilting and it's traveling from BDC to TDC. It's a fascinating design. So when somebody says to you, oh, it's just a cylinder, it is not just a cylinder. It is not just cylindrical. This thing is quite a marvel of engineering, quite a marvel of mechanical engineering in particular. The valley design is very particular as well, and the way it's been designed. These chamfers try to incur a level of deformation. They've tried to make this so that the skirts, because the skirt here, from between here to here, is actually elliptical, and they put these contact chamfers in so they can make that ellipse smaller, so you can run a tighter and more refined run on your engine. Some argue it doesn't work. Some argue and say it's the next best thing since sliced bread, but you just don't know. So anyway, so let's move in. I'm just going to double check, get my inertia calculated, and then run it from there. Now, we need two particular points of access. If we're coming from the top of the cylinder, what I'll do is I'm going to go back to my original model. And what I actually need to do is go evaluate. I'm going to measure between top of the piston. And I'm actually going to try and measure to, if I go to the center of the rod should give me that. So if I go, let's have a look. What do we got? Oh, that went incredibly well. Right, so I'll go again, measure it back, and then what we got is, it's coming off my point. Always keep having this at the minute. Okay, then because I'm not trusting on what that's giving me, I'm actually just going to quickly sketch that construction, that line position. Some of you have probably found this yourself. I find this all the time. I come across measurement tools and it'll go, oh yeah, that's what it is. You go, not convinced. So I'm going to look at that. We have 24.139 millimeters. The reason I got to check is I don't know what my translation is going to be all the way down there. I want to make it central so I can get the rod to sit into position. We can run through this and then decide if that conrod needs to be there. If the gudgeon pin, needs to be there. But as I said, we know that that is our fixed value of 24.139. I'm going to come back. And for this, interestingly, I'm not adding anything yet. Will do soon, but not yet. Oh, well. Yeah, I will do soon, but not yet. So I'm going to click apply and then just close for the minute. Oh, I've left my R turned off. I'm going to come back, go to my diffusions onto frames, turn my R back on, click F5. I'm going to change this color because, again, this will become confusing. So drop into here and I'm going to change this color. I can actually change it back to a gray. With this now, it just means that it remains separate, if you will. So let's connect that up. Now, obviously, if I now go to what I've got, that's what it gives me, which is not good at all. It's a pain in the backside, in fact. So arguably, oh, it's just happened to me again. I have no idea. I have no idea why that just happened. I'm starting to think this is me that's causing the problems, which is not good. Again, don't worry though, this is fully recorded, and sadly, you're actually going to pick on that going wrong, which is brilliant. I don't know why it keeps cutting out, but it does keep cutting out. I will investigate that later today. Right, so we're now in that position. It's not good at all. What we've really got to do is decide how we're going to solve this one. Now, I did suspect this when we were putting it together. I suspected this, but we're going to use that top crown as a reference. But if I put on my toggle, you see there, see how my Z is here? Even if I transform it down, it's going to be a pain. I could transform it down and rotate Y. Yeah, I could transform it down and rotate Y by 90 degrees. So yeah, in fact, let's try that before anything. So if I go translation, let's go rigid transform. And from here, what I'll do is I'm going to translate my Y by 90 degrees. And I'm just going to see if I get something in the right position first, before I even start trying to get this right. So now we're in this stead, which is still not the best. Okay, so that's still not the best. Right. So, tell you what, we're not. I'm just thinking, do we keep doing rigid transforms? Let's just put on a new frame, because I think that art is not going to do us any favor at all. I think if we put on a fresh frame, that will fix our initial problem. So if I go frame and I go to the same thing again, and this time what I'm going to do is I'm going to say use selection. I'm going to call it connection. You see here, I can only do this if I have a frame that I've added. The system won't allow me to change some of its own predefined frames. So what I'll do is I'm going to translate. This is going to be very tricky. I'm going to translate my Z. No, I'm going to translate my Z to my X. So I'm going to drop this. I'm going to go to my X. And it goes, whoa, 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 whoa. You've got one primary axis here and another primary axis here. So what it's saying is that axis and that axis are vital for it to understand. The third axis, it knows that will be relative to these two. So then it's just saying, I have no idea what you want me to do because that's impossible. So what I do is I drop this and I say, right, we'll make that on the Y. Then what it does now is it places me a Z in this particular component, which is nice. We do need to be clear though about where this is moving, because this is what poses problems as we're going through and issues as we, as we gradually make our way through it. If I come back again, it just makes me wonder if I can do something else to flip that up as well. So if you see where my Z sits, oh, hang on a second, no, I just added, I didn't mean to do that. You see where my Z sits, it sits there. If you look at where the actual thing's sitting, if I could flip X and Y around, would that make life easier? And in essence, yeah, it would. So what if I say, no, that's not going to do it. Let's have a look. I don't think that's going to fix it for me. That was brilliant. That did nothing. I'm glad I did it. I'm just being facetious. Minus. No, it just brings it all back to the original. So what we're going to do is go positive. Oh, positive Y, sorry. And move that to a negative X. Is that going to help me? Oh. So what I'm essentially trying to do is just get it so it'll give me something that I can work with. Now, I can work with this. I was just trying to be lazy. I was trying to simplify that as much as possible. This is one of the results of when. Oh. Flip that round. This is going to be awkward. Brilliant. Right, so this is coming now. So my Z, I'm wanting my Z to go through this axis. And because I've been messing around, I've obviously left the Z in a different component here. So let's have a look where we're sitting. My Z in this state sits... Oh no, look at that. According to this, my Z is sitting correctly. Sitting down here. So these should be moving here. So it makes me wonder, it might not be that. It might be me adding stuff in there, trying to fix it. My God, I don't even know how I fastened my shoelaces this morning. There we go. So we're in essence back to what it was. And what I'm going to do is rotate around Z 90 degrees. Now I'll go minus 90 because that's where I want to move to. So I'll go standard and I'm going to go minus 90 and then apply. And then that should give me that. I almost want to cheer myself on. I really do. Right, so we now know that we're the central point sitting there. And we know that our offset was 24.139 millimeters. So what I do now is come back in. I'm going to go my translation, and I'm gonna hope it's going to allow me to do this. So I think it should be X, but this is where I'm just going to play around a little bit. So when I'm translating this, I think I'm going positive X, or it might be minus. Oh no, I'm going minus X. I'm going. So with this, I'll go 24.139. 24.139. Then apply, and then we're going to update. Apologies, it was positive. There we go. So let's just take a quick look at where we're looking. There we go. Right. So let's just run it and just see. Right. Now this is happening because if I just flip onto here, look at where Y is moving. Y is our gravity in this case. And it now sits in X. Now I've just realized that's going to prove to be a bit of a tricky one, isn't it? Look at that. You look at where that's sitting. It may have been better to try and sit this into Y. Let's just try it. Let's just try it. We may have to move that around, I think, to Y, just because of its offset from the initial center. But it's all right. Once we lock that in, it should allow us to move. Now, this is the bit that catches me out every single time, every year, and gets super embarrassing just because I kind of think, the hell is going wrong here? So, where my translation sits now. So I'm just going to sit on, I'm just going to go to the piston on my tree and then go frame. So that's where my translation sits on the frame once it's finished. So if I go to rigid transform here, so go to rigid transform and go to follower, that is where it finishes. Right. So what I'm going to do is I'm going to need to rotate this by 90 degrees. And this is the same sort of example as before, if you remember. What I want this Z to be is I want it to point upwards. The only way I can do that is to rotate it 90 degrees. So I'm going to bring this across to here. And I'm going to connect that up. Just going to check that. I'm going to remove my translations because obviously I don't need translations now. So I've removed my translations and let's have a look. I'll go, let's see, X. I'm going to go negative X, apply, and then let's just take a look. So on my rigid transform 2, base, follower. That's what we're after, because that allows us now to have that cylindrical behavior. You'll notice at the minute, I've still not added the rings. I will add the rings. But for the minute, I'm just trying to get overall geometry up and running. As I said, beauties with these now, I can run these in and you can do catch-up. You can do it at your own time, your own pleasure. I'm trying to do these now to be specifically aimed at the assignment. So you'll see here, the issue with this is the axis. I particularly chose this because I knew that when I was first constructing this on first generation, getting the axis right was very difficult. And I should have practiced it first, won't lie. So I'll start off with my standard. So I'm going to go prismatic joint. I can drop in cylindrical, 100% drop in cylindrical, but I'll start with a prismatic joint. Where is my prismatic? Prismatic. Going to use my prismatic, and I'll go from base to follower. So I'm going to flip that round, and I'm going to join that to there. Don't forget at the minute, if you haven't done, save this. In fact, I'll save this myself just because if I don't, there will be tears. So I'll go KTM 525 example. Put it on there. I zip the, oops, these spaces. I normally zip these together, so when they appear on Blackboard, you can download them as that. So I'll save that. Now I know I'm moving really quick here. I'm trying not to because I'm just caught in this mindset of the time. So is there any questions on this so far? Brilliant. Again, you can interrupt at any point, any time. Please do. But I'll just keep going. So, with this in mind, I should now be able to add another rigid transform. Now, if you remember, what I'll do is just connect this up to the base. If you remember, I'm coming from the base and I'm trying to match the same positional frame between here, well, I should say between here and here. Let's just drop all the translations at the minute. It's not straightforward to do this, but I've been trying to come up with the most creative ways of being able to map these frames. So I saw one the other day from a student who was doing something like this, and I thought it was a great technique. So I'm going to steal his technique. Let me have a look. Let me come back across here. And then what I'll do is go prismatic. Oh, just dead. Get up to here. We're going to go prismatic. Prismatic here. So I go base, follower. They're obviously going to go in the same position. Now, the beauty is, see this frame, rigid transform 3. If I go to rigid transform 3 and I go base, and I go follower, that is what we need to be aware of. So we need to make follower from rigid transform 3 and follower from prismatic meet each other. When they meet, it will be fine. All the translations will be fine. But we've got to make these two touch, which sounds weird. We've got to make these two connect. So first things first, let's just see on which frame we're talking about. So I go again, follower from the prismatic. See, we've got this translation across. We can work this out. So I go to there, and then to there. Okay, so then if we go from the top, I go from the follower to follower. You see there, we've got an X and Y key component there. So, with that in mind, then let's track these back together. Let's push these back into position as they should be. If this, because this should now meet along the X component. Onto this point here, we knew we'd rotated and we knew we had rotated minus 90 degrees. So I'll go X, we know standard arbitrary, minus 90. So then apply. Then I'm going to update. Now, as I said, I saw a student doing this. I thought it was a great way of doing it. So we've got this now faced in this position. Look at the follower from rigid transform 3. I'm going to go follower. Now, you look there, still not meeting like I wanted it to. So follower to follower. We're still in the wrong position. So I'm going to go back. And now I'm going to try moving it in the positive. So I'm going to update. Follower to follower. Still not in the right position. So if I go Y, what do if I go Y? Apply. Follower to follower. So what I'll do is I'm going to turn that off again. I'm going to have to remind myself, actually. I don't know what we'd had there. So go follower. Follower. So let me shift that in the Y. And then we apply. So that's come around the Y. If you look there, the Z's in the right component. So if I then apply that to here, so the Z is in the right component. However, if Z was rotated by 90 degrees, it would then work. you've got to admit that it would work. So what I'll do is then bring this back, and then I'm going to add another one in. There is another way of doing this, but at this stage, I don't want to add further complication. The other way of doing this is using almost like a Cartesian behavior. It doesn't work exactly like they want it to. It's not that straightforward, but it does resolve a lot of issues straight away. So I've just applied that, and we go follower, then base. So let me just come back and go minus date. And then with this now, if I go rigid transform 4, because I'm now no longer tracking with that, I've got these two touching each other. So this one is now the one I'm looking for. So 4 and 4. So these two now map the same distance to each other. It's a good start. So if I just connect these, you'll see what happens. It should crash. Please don't work. Oh, yes, it does crash. Now you notice that it's snapped into axis position, which is what we want. However, look, see how that's snapped across? It's because there's still inconsistency. So I'll drop that back out. Now we can look at that translation across, what's going wrong there. So on rigid transform 4, I'm going to go over to rigid transform 4. I'm going to go follower, base, follower. What we need to do is move it across. Now, you could either do it within this single rigid transform, or we can make it even another step. What I'll do is come back in, and I know for a start, I'll drop that, go none. I need to know what that translation from there to the center of the axis is. Easiest way is to go back to the model. If you have SolidWorks, this will make your life a lot easier. Not impossible, never impossible, but it will make it a lot easier for you. It can be just a bit of a pain in the backside having to figure out measurements between it. All I want is a center point here and my key point here, and I just want to know what that distance is. Now, if you look at where it's coming from, it's actually coming from the center of that. Oh, it's actually coming from the center of here. Now, I suspect, if I just take a look at that, I suspect the origin was started there. That's what it always refers to. Refers to the origin of where it is. So it's come there. In fact, I wonder if crank pin. Oh, no. I didn't actually draw some of this. I had a student do it for me, just to make my life easier. And yeah, I was hoping that he might have followed a procedure, but sadly not. So let's take a look at what that distance is. $63 millimeters. It is 63. Oh, makes me nervous, that. So I'm just going to do that again. Okay, I'm going to go external point reference to external point reference, and making that 63. Okay. So what I'll do then is, for this, I'm going to go Cartesian. And I know in this case, I actually want to move along the Z, 63 over 2. So I can do 63 over 2. You literally can do that. So I'll go 63 over 2 and I'll apply. And then let's just take a look. Where's that base follower going? That's what we're interested in doing, tracing these together to make sure that we're getting something a bit more sensible. Now you look there, I've actually moved, clearly there I've moved in the wrong direction. So I thought I was coming along. Now that's Z would suggest it's moving upwards because these are revolving around here. So I've gone in the wrong direction. So if I go, put it in my Y. Why, you say? Because I want it to be... minus. So you see where this is moving around? All I'm doing is tracing to where it's sitting. There. So that is rocking, is it not? That is rocking. Happy days. We are one step closer. And interestingly, because that's now lined up, I'm just interested whether that will actually run. My God, it does actually run because that central axis point is connected. I don't like it because there is errors there, but it does run, which is embarrassing. What I mean by that is if you look here and we come back, I've got that 24.193. I'm going to copy that. It does need to be there regardless of frustration, and regardless of if it runs, it does need to be there because it is vital to the reference, really. Oh, you see how that's moved out? It's me putting it in the wrong place. So let's bring that back, put that out, bring that to 0, and I'm going to place it to the front. Boom, onto there. That should give me something a bit more. Just double check. Just check it. Ah, no, it didn't. That was me doing that wrong again. Does need to be there. I'm saying that to reassure myself. This is so weird. I'm sitting in a room by myself, just talking to a screen. Okay, right. It's better. So we've got that axis point back. Right, so what have we done? We've actually constructed this. The one thing that we haven't done is we've not put on the rings. We can put the rings on. There is a relation for them. They do technically suffer with torque that travels around it. Not a lot of it. There's hardly any of it. But there is something for it to revolve around it. However, first things first, let's make sure that this will run like we want it to. Now everything's now constructed. I'm going to put in some revs. So let's put in a velocity. Let's go 360 revs per second. Let's just make sure it's doing something that we're after. And we're going to bring it back. Bring it back. I'm going to run it. So that means I can put down to 0.8. So run again. Oh, 0.017. Yeah, so we got something there. Now, slow that down. Just make sure you give me something I'm after. Nice. Okay, so we got a few cycles in there. Right. Let me just check my materials. Okay. Now just want to check the position of where everything's sitting. Now, what I'll be aiming to do personally is I'll be aiming to take some verification from the piston, because everybody should know through the calculations that you do when you're doing reciprocating mass, a good point for verification is actually at the piston or the gudgeon pin. So what I'll do is I'll first set that up, and if I come across and then go, sorry, I've gone to the wrong spot. So if I go to my simulant library, bring that back across. And what I'll do is go to my forces, my frames and transforms, go rigid transform, bring that back in. I'm going to connect that up. Now, anybody who's unsure, we did this in the linkage, bar linkage. I need a reference point, so I'm going to bring in my world as a reference point. I could use a reference frame, but that just depends how I want to measure it. But this will measure it relative to where it sits, which makes it a bit easier. I'm going to double click in, and I'm going to go translation. So with this, I just need to be sure about where I'm moving. So I'm moving on the Z, on the X, sorry. So I'm going to get translation on the X. Translation will give me position. I want velocity. And I want acceleration. These are the 3 key points. In it as well, I need to give some appreciation to the references of joints. So it needs some damping, because to assume that there is no damping or any type of coefficient of friction between it is negligent, some would say. You'll notice here I'm using a specific value. What if I just go on here and then go into my model space and then just add damping? If I spell it right. And then on here, I'll go 0.001. Now that I've got nice reference, I can go straight in. I can just put in damping all the way through. So I've got damping. All the way through my joints. And now I've got a behavior of these straight away that is governed by one simple variable. And it makes my life so much easier. Right, so we've done that. Let's just double check that I've not made any mistakes. Anytime you change something, always run it again just to be sure, or else there's going to be upset moments, you know. Right, so come back to my my Simulink library. I want to go to Utilities, and I want to go to PS to Simulink Converter. As you know, now I'm at a point where I need 3 as a reference. So go 1, 2, 3. I'm going to bring you into here, bring you into here, bring you into here, like this. And then up across, and that'd be great. Something like that. Okay. Right. So I'm going to go back to my continuous, commonly used blocks, and I'm going to go scope. 3. I'm going to come back down. Add you here, add you here, add you here. Right. So I'm going to name that pos or position. Gonna go, is it velocity acceleration that I chose? Velocity acceleration. Velocity. And then I'll go acceleration. And then I will run it. And let's have a look at the sample set that we get. Because this allows us to look also at, wow. Wow. We need to separate this. If you remember, I need to separate this to 3 separate component sets, or else what it's going to do is it's just going to go crazy and not quite right. So if I then zoom this up again. Right, so my method, I mean, really, I could run this for what? 0.006 of a second. So let's go 0.006. 0.006 of a second. 0.006 of a second. And then if I run it down and make the data sample a little bit. Now, there we go. A little bit more like what we'd be looking for. I'm just going to tidy up that. So I'm going to go to simulation, model configuration parameters, and I'm going to give myself a little bit more time frame on it. So I'm going to increase my tolerance that it'll allow it to go to and go to 5. That should just trim out any noise that's occurring from accuracies. So now we've got this smooth transition between it, but look at this flat. This flatness here would suggest that the conrod between them The rod's actually quite long in comparison because you can have differences. Now this is going to flow quite nicely into something I did want to discuss with you. So I'm going to minimize this and minimize this and minimize this and maximize this. Lots of this, lots of that. So I'm going to go to my lecture notes and just give me a second, because what I'm going to do is I'm going to pull out a particular, where is it? There it is. I'm going to pull out a particular example. It's quite nice as just an example, that's all. It's just something that I've written quite a while ago, really. So engine work, let me just look what I got. So go position sets. Let's have a look at position sets. Right. So now this is one that I've done. Now this is all the theory-based calculations for everything that I've done studying this particular type of engine, looking at crank radius conversions, relative speeds, looking at the length of the rod, the length of the crank, and the calculations that I've used for the position, the velocity, their acceleration. You do have, I was even comparing Wikipedia versions to Stone's equivalents. I actually found they weren't that much different. There was some changes in it. So if I just run, this is all coded, but if I run, let me just add that to path. Let me just run that. And oh yes, that's my cylinder deformation. And there's my abrasive. There we go. Right, so particular output performance, and you see this bump? This bump actually emerges from the relation of the crank, the LNR ratio. But what we're actually interested in is the offsets themselves. So I want to really try and map that against it. So looking at that, we're going, because this is in meters, so it's about 6, something like that. You look here, just above. This is a curve. I mean, I'd gladly map it if you wished. This is a curve, and you actually look at my physical calcs against simulation, and I'm near as damn it. This is just to do with, I've calculated this from a different position. This is assumed to be 0, as this is not. This is just because it's moving in a different plane. This is absolute. But what I'm interested in is that relation. My velocity, the curve, the skew between it, I'm getting that skew. So if you look at my 0, I mean, yeah, so I'm actually quite pleased with that. What I could do, if I wanted, I could now start to look to take this out. Wow, that didn't go right. There we go. So what I could do is I could now look, I could take this plot out. So what I really want to know now is, if I'm happy with this and I'm ready to do something with it, I'm going to actually take this out onto the main space here. This is all the variables that have come out of my simulation. So what I'm going to do is go back onto here, and I'm going to go to Simulant Library, and I'm going to go to here, and I'm going to go Workspace. Because if I put a scope plot in my assignment, in any work that I do, people look at it and just say, I'm sorry, but that's incredibly poor, and you will be quite badly treated for it. So I'll call this position. So what you're best doing is turning it into something quite attractive, something that people look and go, I understand that, I quite like that. So I've got that in, I'll run that again. We come back, scroll all the way to the top. Where is it? Where is it? Where is it? Wow, look at all this. I'm just going to get rid of all that. Gone. To run that again because I don't know where the hell that's just gone. So I'm going to run that again. See where the outcomes. The outcomes. If I click onto out and then click onto plot. There we go. I didn't think it was ever going to come. Oh, that was a bit rubbish. So I'm going to double click into out, and if I click on my actual position, and then I was hoping I could do it from top level, but apparently you can't. So click onto top level. Now what we've got is a nice plot. I can control these values. I can control the font type. I can control the units. These on here by simply clicking on here. And then this allows me then to move towards a little bit closer. If I want this to be exported and put into MATLAB, so if I go save as, I mean not MATLAB, if I want to put it into my work, if I go save as, and I'll just go an enhanced meta file, and I'll call this example. And I go save. I'm just going to go on to new document, and what I'm going to do, go blank, insert picture. You see there, when it comes in clear. But I mean, obviously you need to change these font sizes and get that different. But that allows you then to plot in, and it looks dead professional. If you give me a scope, it isn't worth as much. You are docked because of it. It's a poor way to represent it. Right. So we've now gone through a particular way of verification. Again, all these equations here, all I've done is group them together. You don't have to use MATLAB to verify it. Don't worry. What I'm saying you could do is you could do it in many other different ways. So you can use Excel. Gladly use Excel. I have no issues with that at all. Now we're happy that this thing is constructed. Let's do some further modification to it. I do appreciate I'm running over, but nobody's booked this class. So I'm going to double click in, and to tidy up, I'm going to drop that R. The only thing I haven't done yet, still not added the rings. Let's take a look at the actual system. Can I add the rings in an easy way on here? Probably can. So I'm going to go to call this compression ring. Use base by selection. I'm going to zoom to my particular aim, so here. And for argument's sake, I'll just say that. So I'll use that, and then say save. And then I'll use oil control. Now, if anybody's really, really, really curious with this, what you could do, you could offer variation in the relation of these frames. Now, that is how I did it. I was able to just offer slight variations with a variable rigid transform, and that's what solved it for me. It made my life so much easier, so much easier. So let's bring in the rings. So I'll go on here. I'm going to rename that compression. Now, because I've given really long names, I've got myself confused. What the hell? Yeah. There's my compression ring. And I'll do my oil control. And then I'm ready to run different tests. I can do all sorts of oil control. Oh. Oil control. And then I'm going to put on my ring onto here. Then all I'm going to do is come to here and now add both oil control and my Molly inside lead. So I'll do the Molly lead design, so F5. And then from my Molly lead design, this is actually grey cast iron because it's in molybdenum disulfide. One of the systems getting resolved on the frames. Oh, on the frames. Yeah, the frames. It's having a whinge because purely I've balls things up on the frames. The frame set here is actually not so bad. We could try attaching that. We'll try that at first to see what happens. Yeah, it's not steel. It is not steel. It is grey cast iron. But for this example, it'll work out pretty well for us because we could test it. We could just make sure this is going to give us something like we're after. I'm going to go into oil control, repeating the same process again. And where is it? There it is. So go to oil control, and we'll go F5. It's going to ask about the frames again. It's not going to be happy. So I'm going to remove that frame, turn on my R control, and then apply F5, update, and then let's connect you into there. So spin that round and connect. So if we come back to the actual engine itself and then add that on. Let's have a look in. Now we should be starting to face the issues I actually faced. Now look here, it's sitting above. So what we could do is go in to the actual original, on the original one here, and say the easy one on this one, the easy fix on this one. Oh, no, in fact, I've neglected this. So, oh, that's connection. I'm looking for compression. Look at this. I've left the Z in the wrong position. So the first things first, we want it to be on the Y component. So it will revolve. Because in essence, if we're going to get revolution, it's going to be purely onto there. We'll go to oil control. We do need to do the same thing here as well. So I'll go Y and save and apply and close. Onto here, and I go here, and I'm going to update. Right. This tells me that my R representations aren't going to work. So I'm going to add in another frame set here. I'm going to add onto here. Here, there we go. We'll call this connector or connection. Use best selection. I need to make sure that my Z is in the Y component. So I'll go Y. So now you see it's going to match against the piston. Spin that round. And then onto here, repeating the same thing again. I'm going to come back on and I'm going to go to my connection. So I'll go from the top, see where this is coming from. This is what I don't know. I mean, at the minute, yeah, I'm not sure where this is going to end up. So I'll go connection. So I need to apply this and see what happens. So onto there, pull it into my Y component, and save, apply, okay. And drop that out, and I'm going to spin that round. So I'm just going to run it. So that's sitting right, and the oil control ring is sitting right. Boom. Happy days. Right, so the last thing I really wanted to do, just to give this engine full appreciation, is I wanted any vectors that are emerging between these two relations as the engine is spinning like mad. I wanted to make sure that I was going to get revolute joints on it. So I'm going to drop on my revolute here and drop on a revolute here. To tidy it up on my inertia frames, I'm going to drop my R. I don't need it. And if I come onto my oil control ring, go frames, drop the R, apply, 5, don't need it. Then let's just run it. Sweet. Perfect. So that freedom to be able to move is present in there. Arguably, as some have told me, which is true, if you were going to do this more, you'd need a planar axis because it needs to be able to twist. Compression rings will torsionally twist when they're in action, when they're actually being used. So what I'll do is I'm just going to come over here. This is getting messy. So I'm going to right click, create a subsystem, and simply call that piston assembly. That's piston assembly. Okay, so I bring that down, rotate that round, and it just makes life a little bit easier, does it not? Bring that down a little bit more, bring that to there. Now, so I'm going to do this here as well, and just call this conrod. Create a subsystem, drag this in a little bit, and just call that conrod. See, what it then allows me to do is do the same thing here. So if I revolve that round, bring it up to here, it just means that if I extend all to there, and then just call that, create a subsystem, bring that down, spin that round, drag it out a little bit, and call that crank. So we've done all this, but we still don't really have a lot of an analysis work done yet. So I'm going to bring that back up a little bit. And then let's start to do that. So the engine, this engine in particular, can operate at around, I'm sure it is 20 Newton meters. It can generate directly out on work, and then you get your initial reactions. So I'm just going to try that. So I'm going to go to actuation. I'm going to get motion to be automatically calculated. What I'm going to do is I'm going to feed in a calculator. I'm going to feed in a particular torque value. I'm going to bring that to there. And then what I'll do is go back to my library. And I'm going to go to my my PS Simulink converter. Simulink to PS converter, sorry. Bring that round. Drop that down to there. I'm going to delete that in. Now we know this has to be Newton meters. Has to be. Bring that in. What we'll say is, in fact, I can pull it from the list. Yeah, pull it into Newton meters. And then I'm going to go back to my library, and I'm now actually going to use a signal generator. I can almost rev the engine, if you will. So I've got sources, signal builder, not signal generator, apologies. I can choose how long the engine runs for. I can choose how it behaves. So what I'll do with this is I'm going to rename that. I'll call it torque out. And well, let's not do a gradual. In fact, I'm going to remove that completely. And I'll rename this and call this torque. And click onto here, and then I'm going to shift this. Let's go 18. Well, I think it was 18.59. Something like that. But it just allows us to feed something in, and then we can take a look at it. So it's 18.59 Newton meters being fed in as torque, and we can look at what's initially going to happen. So I'll run it in. Let's see how the engine responds. Yep, that was short. If I then just expand this, sometimes you want to see the whole thing. I'm just going to change it to a 4 split screen. And then if I run it again. Okay, so we're now running at that particular state. Let's just check the actuator joint, do some sensing. Let's go for position, velocity, acceleration. No point pulling out torque. We fed in the torque, so we should know what that's going to be. What I'll do here is come across. I'm going to borrow that because that looks like a good configuration. Of course it is. I'm just going to come up and rotate that round. I'm going to feed in here, into here, into here, and then run. Interesting. Acceleration on this. Velocity declining. Position really is not going to do an awful lot. It's just going to get bigger and bigger, just because it's just measuring about this. It's not really taking anything out from there. Let's see if we can make the coefficient of friction less. Let's see what happens when we drop the coefficient of friction. What we should get is a more aggressive, quicker response. So let's run again. Look at the positional climb. Look at the speed. Look at the velocity between the two. We're getting a lot more of a vicious response. Let's push this to 1 second. Arguably, is it quick enough? So let's run it again. See here, now this velocity decline. So it's spun up quickly and then it's just declining onto it. This is purely coming because it is settling. And this is also coming from a decline as well. So let's run it again to even more. Let's go 20 seconds. So, how's it looking? So let's just take a look once the engine is spun up. If you look at this, acceleration, reach, because obviously your velocity is the rate of it and the acceleration is at the pace of it. So if I just extend onto these particular points, extend it in, extend it in, extend it in. Oh, let's just bring that out a little bit. I've come in a bit too close there. Let's bring that out. And to just over a couple of seconds. Now that is what we're particularly looking for. Looking around this. Now we've got to reverse what appears to be an RPM of around... Yeah, it's moving relatively quick. Moving relatively quick indeed. I mean, the positional offset is what you'd imagine. It gets to a particular point and then will hold its own. What I'll do then is, I wonder what happens if we assume that the engine has suffered quite a bit of damage. And damping in this case will stop that joint from being able, will stop all joints from being able to respond successfully. So this is the engine under very fixed states. Look at this. This is quite good. I quite like this. Let's zoom that out. Total decommission. Totally dead. It is, in essence, rusted. I wonder if it's even giving me anything useful here. Look at that. Phenomenal. So that then makes me think, right, okay, let's go back to something a bit more sensible again. Let's stop being daft. Or being daft. I'll bring that back in and drop this again to something that's a bit more what we'd expect. Now, what I really want to see now is I'm going to come back to my rigid transform, and I'm just going to see if... No, I was expecting the old frame sets to be there, but I'm going to go on to my forces and transforms. And Now, somebody told me yesterday there is a force sensor, and I was just seeing if we could actually squeeze that one in. Doesn't matter if there isn't, we can do this another way, but I was just curious myself as to just see. Self-force and torques. Let me just check on this. I don't think that this is internal. I think it's all actuation. It is all actuation. Yeah, it's all right. It's all right. I was just curious, really. Right, so we're going to come back, and the transform sensors and translations don't really give us much at all. So what we'll do is we're going to have to pull off a force. Let's see what we get from the total force from here. It may be this would need to be verified. Now the calculations I was showing you earlier, it does verify all forces as well. If anybody's curious where to get them from, or a good way to find them, Richard Stone's book on translate on forces on not bloody forces on internal combustion engine fundamentals is phenomenal book for be able to doing stuff like that. So I'd always recommend it. Now, when this comes out, it always comes out as total primary and secondary forces. So what I'm going to do is go to my rigid transform, and I'm going to bring in what they call a DEMU. So I'm going to type in DEMUX, or DEMUX as many know it. So I'm going to drag in a DEMU. I want 3 inserts, and I'm going to bring that DEMU in. Bring this across. Oops, whoops, that nearly went horribly wrong. Oh, yeah, what am I talking about? So, in fact, here, these are all severed. Whoops, that's me hitting the wrong button again. So, these are all severed. Now, if you remember, it's just to do with the inputs. And it's because only one of these is really needed. So if I just click onto here and I bring in this and then shove that onto there, then connect this up to the forces, and then all I just simply do is connect them up. And what it will do is, because it brings in these 3 forces, it will split that signal into 3 separate pieces. So let's just have a look at what type of forces are being produced around the prismatic. This will just give us axial forces, and it will be plus and minus relative to what will be, let's have a look, will it be our X? It is our X, isn't it? Where are we moving? Yeah. You look at our engine here, it's only moving on the X. So let's take a look. Yeah, it is particularly what you'd expect. This is going to give us our maximum outputs. We have noise that emerges because it's coming from a component which isn't being used. But these 2 are our key players in all this. So our XYZ component sets. This is our key players in all this. So I'll just expand here. Oh, that's a bit okay. I'll just bring that back. Every time I do that, it just doesn't do what I want it to. Bring it up to there. And confirming just under 3,000 newtons, of force in that particular point. Again, it is very, very right. I mean, if you do verify this through Stone's handbook, you can verify it. So let me just see what I can pull out of mine. Have I still got it open? Oh no, I don't have it open. It's not too far off, to be honest. It's very similar to what you get, but the trouble is everything's been put into a prismatic. Further analysis on that will allow us to drop in a cylindrical. We could look around the piston rings as well to see what's happening there. But now that's it pretty much, boys and girls. So I know I've run 20 minutes over, and I know my PC now is having a meltdown because I've ended up recording way over what I was hoping to record. Before I draw a line underneath that, are there any questions? Have you got any questions that you're curious about? Have you got any requests that you'd like me to cover up again or cover in more detail or anything like that? I appreciate that. Like I said, we've just done a 2-hour, 20-minute build. But this is a little bit more frustrating. This engine itself is not straightforward to construct. Once we've constructed it, though, I hope you found a benefit with it. If there's not any, I was nearly going to cut you off then. My apologies. Oh no, she's deleted. What I do intend to do is keep running these, but I'll keep doing examples with it. I've been told to stay with the timetable, but it makes me wonder whether I should just keep recording these anyway and still do live sessions. After all, we've all been isolated to our houses now, which is a bit weird, won't lie. But so we can use this to our benefit. Again, if anybody's interested, I am going to be doing some extra, because again, we've now got time. I'm now going to be doing some extra videos which will be microcontroller interfaced. Anybody who's interested in my Bill and Ted project, yes, I am going to do some more on Bill and Ted. I do intend to look a bit more about their learning algorithms. I managed to get some, I mean, don't get me wrong, as everybody keeps telling me, it's already been done, but it's a benefit for me. I did manage to use what they call a single perceptron with a PID controller, and it does crudely do some very basic observation learning, which is really, really interesting, really interesting. So I am tempted to do more with that. So if anybody's interested in that, please drop me a line or email or anything like that, and I'll do that. Again, if there's any other questions, please fire away. But what I will do from here is I'm gonna click stop on my record and then get this onto the encoder. I will take this model, I'm going to zip it together, and I will upload it to Blackboard right away. The video takes a little bit longer just because I've got to upload it to YouTube and then hide it in the hidden function. But if there's not any other questions, again, send me a message over Teams. It's only because at the minute I'm being flooded with coronavirus emails about, have you done this? Have you done that? It's like, yes, yes, yes. So if you message me over Teams, you can personally message me, or if you are desperately need to speak to me, you're more than welcome to call me on Teams. Yes, you can call me. You're more than welcome to call me on Teams, and I will do everything I can to try and help you with your problem. If there's not any other questions, what I'll do is I'll log off, and I will see you. Well, I'll speak to you all very soon. Again, any other questions with the assignment, please get in touch. I'm more than happy to help. And with that, dear fellows, I wish you a cheery afternoon. Speak to you all soon.